Hello, it's John Broadwell, creator of the Serial Wombat open source project and a consultant at my company, Broadwell Consulting, Inc. Give me a call if you need help with embedded systems. A couple of big announcements today. First of all, I've started an Instagram page, so follow me at Serial Wombat on Instagram. I'll be giving periodic updates of a lot of stuff that I'm up to and quick reminders of some things that you might have forgotten that the chip can do. Should be a good way to get little microbytes of information about the Serial Wombat project going forward. And a fairly big deal, I have released MicroPython in a pre-release version to you guys so that you can start playing with it if you like. And we're going to take a quick look at one of the examples in this. The examples are not fully filled out, nor are all of the interfaces in terms of UART, I2C, the way that you can talk to it. And so far I've only tested it on ESP32 and on the RP2040 Raspberry Pi Pico, but it seems to be working well there. So you could take a look in the GitHub repository, Broadwell Consulting Inc. /Serial Wombat MicroPython. And you can see there are just an enormous number of files here, each of these translated line by line from the Arduino code. I posted about that a little bit earlier. So it is C++ code that's been translated into Python. So some of the code looks a little bit C++-y or may not follow the most common ways of passing parameters or some of the other things. Another thing that I realized is for MicroPython, I had to give up enumerated types. And so there's a number of enumerated types that are no longer available. And so you have to look in serialwombat.py to see the values that would be used normally for those enumerated types. But other than that, it exactly matches the interfaces from the C++ code. All of the modules are available. All of the function calls from the modules are available. And a good number of those have been unit tested. So as you know, I have a unit test board that I created that runs Serial Wombat 4B chips against a Serial Wombat 18AB chip, plus against a voltage generator to test some of the analog and resistance pins. So that unit test is working for all of the modules that have currently been tested. That includes analog, the communication error method, debouncing, echo testing, frame timer, high-speed clock, high-speed counter, PWM, processed input, pulse on change, pulse timer, quadrature encoder mode, the output scaling functionality, servo output, UART, software UART, and that one is all test code right there. So let's take a look real quick at the Serial Wombat MicroPython code. There's a couple of files that you're absolutely going to want to have. Serialwombat.py is essential, as is serialwombat.pin. And then you'll need Arduino functions.py as well. What this does is essentially puts an Arduino-looking wrapper that uses the same names like delay and millis around some of the machine functions or time functions for Serial Wombat or for MicroPython, so that I can do the line-by-line comparison and keep things as similar as possible. So, and you'll need to pick one interface. So in this case, I've got a MicroPython I2C interface, and essentially what that does is it inherits from the Serial Wombat chip class and overrides a couple of functions to send and receive data so that we can abstract out the type of interface. This is a little bit different than the way the C++ class does it under Arduino. That class incorporates both UART and I2C with the selector, but that wasn't going to work well for Python, and I may go back over time and push the Arduino class in this way as well. I like it. So right now there is one example that is a really good example to look at. If you go under Examples, WS2812B, and into First Test, you'll see this Python code, and we'll take a look at that now in Thonny. So here I've got Thonny set up, and it's attached to a MicroPython programmed ESP32 board. We'll take a look at that in a minute. And in order to be able to, the example we're going to want to run is that WS2812 example. And in this example, we import Serial Wombat. We import the interface that we need, which is the MicroPython I2C interface. We import the Serial Wombat WS2812. That's another difference between this and the Arduino. In the Arduino, we pull in all the .h files as part of Serial Wombat.h. They're included at the bottom. You'll have to explicitly import the classes that you want. We didn't want them all tied together because that can, basically that takes up RAM and processing for the MicroPython since it's interpreted, not compiled. At least that's my belief. I'm not an expert on Python. If I'm wrong about that, let me know. So, and then what you'll want to do is just declare an I2C instance from machine, tell it what pins you're using. Frequency, you'll want to set that to 100,000 every time if you're using the Serial Wombat 18AB chip. It does not support 400. If all you're using is Serial Wombat 4Bs, you can leave that alone. Timeout, I haven't played with that. That probably needs to be a lot shorter. Not that we typically get those. Then you instantiate a Serial Wombat chip by calling by creating that, giving it the interface to I2C and the address. Right now you have to set this. That may change. And then I'm going to instantiate a Serial Wombat WS2812. I'm going to say that it's on pin 15 of the Serial Wombat chip, and that there's 16 LEDs attached to it, and that it should use the buffer index of 0. All of this is explained in the WS2812 video, which again is targeted towards Arduino, but that is perfectly compatible because all the interfaces are the same. So if you look up above now, you'll see a tag that goes off to that WS2812 video if you want to watch that. And then to keep the similarity with the Arduino examples, we'll have a setup and a loop. And we're just going to call WS2812 begin and then write the mode. On Arduino, we would have used this enumerated type. Again, int enum is not supported under a MicroPython like it is under regular Python. So I ended up just putting the explicit value in there. And in this case, the loop doesn't have to do anything, so it's pass. And then at the end of all of my examples, you'll see this call setup and then while true call loop. That's an approximation of the executive on Arduino so that the examples look the same. So in order to run this on the MicroPython ESP32 that I've got, we're going to have to upload some files. We're going to upload Serial Wombat. Give it a second. That's kind of a big one, about 50 kilobytes. We're going to have to upload Serial Wombat pin because the WS2812 calls from that. And you don't have to remember all this stuff. If you want, just open the example and hit go. And boom, it will start telling you with the things that it can't find. Then you can add them in and you'll be fine. So we'll upload Arduino functions. It needs that one. We'll hit go. It needs the interface function. And it needs the pin mode file for WS2812. So we'll upload that one. And that seemed to work. So now we will run this. And here we can see our test setup. We've got the ESP32 that's running the MicroPython, and it's connected via I2C lines to the Serial Wombat board, which has pull-up resistors on it and is not in UART mode. Pin 15 is connected up to the WS2812, as are the power lines. So when I ran that MicroPython script, it fired up the Serial Wombat chip and put PIC15 into the chasing LED sequence test sequence for the WS2812. So that's where we're at right now. Pretty excited about that. And hopefully this is the beginning of a lot of really good things. My intention is to port all of the examples from the Arduino example library, and then in future versions of the pin mode videos, I'll be switching back and forth between Arduino, C#, and the Python, because they all have equivalent interfaces. So take a look through the Python code if you can. Give it a try on one of the boards. I'll tell you, it doesn't work on ESP8266s. It's just, I believe it's just too much code for it to try to interpret at one time, even with just the rather large Serial Wombat.py. It does work good on the RP2040s and ESP32s. So take a look through that code. Let me know if you think that there's anything that I'm doing that's egregiously wrong. And, well, there's still some time to fix it before people start integrating this into projects. Or, let me know what else you'd like to see, what other pin modes, things like that. And again, subscribe or like this page, subscribe to the YouTube, and follow me on Instagram. All of that stuff helps a lot. And don't forget, the boards are available for sale on Amazon. Thanks a lot. Have fun and keep making stuff. The Serial Wombat firmware is available on GitHub and is constantly being updated. Subscribe below so that you can see the latest features and videos that come out as we fix bugs and add new features. The Serial Wombat open source project was created by Broadwell Consulting Incorporated. Broadwell Consulting Incorporated provides help developing medical devices with a focus on developing embedded firmware, which is compliant with IEC 62304, ISO 14971, and ISO 13485, as well as remediation assistance for products already in production. For more information, contact John at Broadwell Consulting. Support requests for Serial Wombat should be sent to help@serialwombat.com and will be answered on an as-available basis. Also, feel free to leave your question in the comments below.